Swayam Prabha. Digital India. Educated India.
So, welcome to the fifth lecture of module 3. So, in this lecture, we shall cover today the Autostart's E-Dart, solid ground curing, microstereolithography, robotic SLA, and some other processes based on liquid as a raw material. So, if on the scanning system side, we use flying optics and a sharp laser beam on a liquid bed, and build the part in -z direction, and if the build direction is -z, of course utilize the bottom feeding mechanism, then the already available system is by Autostart's E-Dart. So, this is how the system looks like. The Autostart's Company Limited, founded in 1984, is a Japanese manufacturer of stereolithography systems. The setup of the laser is found under the resin tank. So, this is the laser system and it is under the liquid tank, and of course, this particular window will be a transparent window. The laser beam is directed into the resin which is in the container with a clear bottom plate. This system uses an acrylic resin to produce the models. The model is formed by liquid resin which is cured by laser light beam from below the resin chamber. The platform or modeling base is raised upward each time a layer is completed. Otherwise, the E-Dart system is based on the 3D systems SLA which has already been discussed. The only difference is it is building in upside down direction and utilizing the flying optics. So, here why it is flying optics? Because this is the optics, right? And it is attached on an x-axis, and also this x-axis is attached on a y-axis through the corresponding motor. Assume that this motor is corresponding to y-axis and this motor is corresponding to x-axis. When these motors will rotate, this optics will also move. Therefore, we are calling it as flying optics because the optics is moving. Now, as the optics moves, you can see one very important benefit, that all the time this laser beam will be perpendicular to the bed. Unlike in the case of SLA where we use galvanometer, you remember that when the laser beam falls onto the galvanometer, it gets reflected, and if it is deflecting it away like this, then of course the beam of the shape of the beam doesn't remain circular. Here it is circular, it becomes elliptical, and hence you required some lenses to correct the shape of the beam. While in this case, the interesting thing is all the time beam is perpendicular to the bed and hence no correction is required. Although there will be a very big disadvantage, that as you are moving the whole optics, you have to limit your speed to a certain value. It is because we can't really move this head with a very high velocity, otherwise we may damage the optics. While in the case of galvanometer, the mass of the moving object was very low, and therefore due to the involvement of less inertia, you can really reflect the laser beam with a very high speed. On the other hand, as you are projecting the light from the bottom, the amount of the liquid required will be also very less. We discussed the same thing when we were discussing about the DLP based technology. In this case, the minimum material required will be equals to the layer thickness of the object. Unlike in the case of top feeding systems where there is a big tank of liquid and you have to dip all the time, and the entire tank should be filled with the liquid photopolymer. Here in this case, the inventory is quite less, hence the process is quite economic. As each time the layer is built or completed, the platform goes up and the new liquid resin flows under the layer. Due to the gravity, it levels quickly and we just again repeat the process to build the part. So, like I have already mentioned, the far most advantage of this process are utilization of the top down approach and no need of having any additional optics corresponding to the beam correction. However, as I mentioned, the disadvantage associated with this system is the slow speed as compared to the conventional 3D systems SLA. So, the advantages and limitations of the process are highlighted here on this slide. Our next system will use mask for the scanning. As it is using mask, it will use floodlight instead of the sharp laser beam. Means the light will be definitely monochromatic but not coherence. Then we will use the shape of liquid as liquid wet because there will be a bed of liquid. The build direction will be in plus Z direction and the recording system will be through the top feeding. Such a system is already available and it is called as solid ground curing. So, the solid ground curing was invented by Cubital Limited in 1987 and it is started commercializing in 1991. Solid ground curing is very similar to SLA in principle. When a laser light of appropriate wavelength falls onto the liquid photopolymer, the energy is absorbed, causes polymerization. The polymerized photopolymer will be in solid state, of course. A flood of UV light is used in the solid ground curing as against the pointed laser in the case of SLA. The associated change is the absence of the image scanning. Instead, the flood is made to pass through an optical mask. This mask is nothing but the negative of the region to be polymerized. So, for example, you want to scan a circular part, right? Then we will create a mask of its negative that will have the opaque portion here and a transparent region here. So that when a floodlight falls into it, it will just pass through this section only. The region of liquid photopolymer where the light falls becomes solid. The remaining liquid can be drained and it is replaced and filled by the liquid wax. Now this is something very interesting. We are using a second material for support mechanism. Unlike in the 3D systems SLA which we discussed earlier, the same material was used to create the support as well, which becomes very difficult later on to remove. However, if we have freedom to utilize second material for generating the support, there could be some means of removing that additional support material by inappropriate way. So, an entire area is exposed together. This process is fast, build time is proportional to the height of the object and not the volume. This statement already we have proved in the case of DLP, because each time whatever the size of this circle which you are scanning, if it is small r or it is capital R or whatever the radius of this circle is, it doesn't matter. It will scan the whole layer in the same time. Hence, if you want to calculate the time to build the part in the case of solid ground curing, it will be directly proportional to the height of the object, not the volume of the object. Of course, the power of the laser and exposed time decide the layer thickness. Here in this case, explicit support structures are required and this is achieved by simply pouring the wax in the region not affected by the light. No need to compute the region requiring support and modify the CAD accordingly. Meaning to say, you need not to calculate the triangles those required the support mechanism in the pre-processing. Here you just build the part, remove the remaining or drain out the remaining liquid material and pour the wax over it. Wax will automatically fill the empty space. Hence, you need not to find out where to add material because you are pouring a bulk of wax material here. So, to visualize better, let me just show you the process cycle for solid ground curing. We start with creation of the mask. Of course, the mask is nothing but the negative of the region which you want to cure. Here, this steel grey region shows that this is the opaque region and light will not pass through this region. and only the light will pass through the region shown in the white color here. First we create the mask for the corresponding layer. Then we do the resin recoating. We spread a layer of resin over the pre-built layer, and here you can see the spreading of the layer. It is the top feeding. You are spreading it in the form like a curtain, which we discussed in the case of objects polyjet. In a very similar fashion, we spread the layer of resin. Then after that, we place the photo mask over this. We place the photo mask over the spreaded liquid resin and switch on our UV lamp. When the UV lamp is on, of course, the light will pass through only through this region which is not opaque, and it will not pass through the remaining region. As a case, this portion which is shown here in yellow color will be in the liquid form, and the region which is here in the white color will be in the solid form. Therefore, after curing of the desired region, the liquid resin can be wiped off like this. This is a vacuum blade. It is sucking away all the material remaining in the liquid form on the slice. Hence, you will end up having a small protrusion of the cured layer. The next step is to spread now a layer of wax. The wax is also spreaded in a similar fashion like we spreaded the resin over it. Now, after spreading the layer of wax, it will be having some extra material also somewhere deposited. So, we perform a face milling operation. While performing the face milling operation, the additional material or the additional wax deposited here can be removed, and you can maintain your Z accuracy. Then again, the UV lamp is on, and again the final curing happened through the high power UV lamp. This portion very accurately, and you get the solid part. Now the process repeats itself. We again create a photo mask. We again spread a layer of resin. We again place the mask over the spreaded layer. We switch on the lamp. We remove the remaining material, and then we spread the layer of wax. We do the face milling, and then again cure the part, and the process repeats itself to build the entire product. This video will give you some idea of how this process works. This process consisted of several subsystems, hence can be called as a transfer line. Some subsystems are corresponding to spreading the liquid wax, creating the photo mask, spreading the wax, face milling operation, and then finally freezing the wax material. So, the first step, like in other additive manufacturing process, here also to create the CAD model and convert it into the STL file. And of course, then we do the slicing of the products which we are making here. This slicing data is used to create the photo masks. This is the process cycle which I just explained to you. The first step is usually to create the photo mask. To create the photo mask, ink is deposited in the region where we do not want the light to pass through. Here you can see the black color region is the opaque region, and when it will come under the UV lamp, it will allow only the light to pass through the region which is transparent to the light. As the region got cured where the light get passed through, the remaining portion will be in the liquid form only. The meanwhile, when we are removing the liquid region, the photo mask will be created on the another hand. We wiped off the liquid material, and as a result, you will have a thin wall structure in this particular case. Next step is to spread the layer of wax. After spreading the layer of wax, we used to have a cold plate that makes sure the wax got freezed. Then a face milling operation is used to make it uniform on the top side. Then after that, the process repeats itself. The steps are, it spreads a layer of the liquid resin, and again the curing happened, and the process repeats itself continuously. After completion of the part, you have to of course de-wax it, meaning to say you have to remove the wax like material, and as a result you will have your final part. So this was about the solid ground curing. In this process, the entire layer is addressed in one go. Hence, the process is very fast. This high speed allows production like fabrication of many parts or large parts. Here, no post curing is required as the photopolymerization completely happen in the machine itself. So why we do the complete curing here? Because there is no support material of the same kind. And we know that as the support material is wax, we completely cure it there itself. Milling step ensure the flatness of each and every slice. Therefore, this approach makes the process very accurate. Supports are obtained by filling the wax after sucking the liquid photopolymer, hence no extra support is required to be generated in the part, and therefore the removal of the wax is quite easy as compared to the removing of the similar material like we do in the case of SLA. However, there are few limitations of the process. The process has 2 cycles and many subsystems like masking cycle, polymer spreading cycle, polymer cleaner, wax spreader, wax cooling plate, wax head, vacuum suction chip and all. Therefore, it is very less reliable. Furthermore, this feature requires a very full time operation attention. If you will not use the machine, the wax may get clogged some of the pipelines and it will become very difficult to clean the entire machine and bring it back into the running condition after some time. Building time depends only on the height of the part and not its volume. The dewaxing time is bit time consuming. It creates lot of waste of the wax which cannot be reused. Our next process uses flying liquid. A sharp laser beam on a liquid wet build the part in plus Z direction and utilizes the top feeding, and hence it is called as microstereolithography. The typical setup for microstereolithography which we have found in the literature looks like this. It used to have a laser beam which got a focal point at a particular level on the liquid wet. Now, instead of deflecting this beam by using the galvanometer like in SLA process, here in this case we will move the entire liquid wet on the XY table. So there is a XY table here and we can move the entire tank on it in both the directions. Even in this case, the Z axis is it attached with the build plate, and each time after completion this particular bed will go down and hence the new layer of the liquid will flow over it. So why we are calling it is really microstereolithography? It is because as there is no galvanometer, there is no requirement of the shape correcting lenses, and hence you can really make a very tiny spot at these locations or at the focal point. Now, as all the time the laser is falling perpendicular to the liquid bed, its spot diameter will always remain consistent and in the circular form. Therefore, you can produce very accurate part by this. However, the process is very slow as compared to the other processes we discussed so far for SLA. It is because here you are moving the liquid bed. Moving a liquid bed may not be a very wise decision. It is because when you move the liquid bed, there may be a chances of producing waves in the photopolymer liquid tank. However, it can be reduced by moving the XY table with a very low speed, but this we will do with a compromisation in the productivity. Here in the work of Besserer et al. In 2001, the resin was mixed with the ceramic powder and then they were able to produce the parts out of it. However, this system is not really very popular. I am showing it just for the sake of completion of our classification so that you can have an idea What will happen if we have the flying liquid bed? Means the liquid bed itself is moving. You will get a good accuracy, but you will not be having a very good production rate in this case. Now let me discuss some of the very interesting and the futuristic SLA processes such as robotic SLA. In the case of robotic SLA, the system I am going to show you uses a flying optics, a sharp laser beam, uses liquid wet, build the part in variable direction. Meaning to say, the direction of the build is not like plus Z or minus Z. It can keep on changing based on the requirement. However, the feeding mechanism is not at all there, but I am writing it as top feeding because the material is available already from the top side. Let us discuss about this system. So, from the work of Pan et al. In 2014, I have got this system. So, what they did, they just mounted a laser head on the robotic arm. So, for example, this tool is your robotic arm. It is attached through the flexible optical cable, and the laser is traveling inside this cable, the optical cable, and then comes out from here. Now, what happens when you are building the part? For example, this is the part you want to build. The entire robotic arm is dipped inside the liquid resin. And if you want to change the direction of build, you can change appropriately by moving this robotic arm. Why it is required? Because consider this part to be produced by SLA. Let me create this part here outside. If you produce this part by SLA, the support mechanism will be required, of course, in this region and even in this region. This is because you are building the part in only plus Z direction. Now, if my tool is inside the liquid wet and I am able to tilt it appropriately, the support may not be required. It is something like this. You want to build this curved surface, and this is assumed that your robotic arm, on which on the tip of it the laser light is coming. Now, if I build like this, of course some support will be required, otherwise I will not be able to sustain this particular material at this location. So, what I can do, instead of projecting the light downward like this, I can tilt this and project the light in line or tangential to the surface, this particular surface, and then I keep on building it, and hence it will grow in this direction, right? If I change the direction, the grow direction will be different. If I change the direction, like I will keep it vertical always, the grow direction will be in plus Z direction only. So, by appropriately tilting the robotic arm inside the liquid wet, I will be able to produce the parts without any support mechanism, and that is what they demonstrated. You can see this particular case where they build the conical shape part, which is at an angle from the horizontal, and they build it in this direction. This is the direction of the build, and you can see it is neither plus Z direction or nor the minus Z direction like was discussed in the other cases. Here it is variable direction depending on the feature. As a result, they are able to produce the part also. You can see this particular part. It is having a slant angle and it was built without any support mechanism. Not only that, they are able to build even horizontal features. Like you see this, after completion of this cube maybe, they deposited these horizontal walls. And there is no support here, if you notice. Conventionally, if you build this part in this direction, of course, some support mechanism will be required here. But as you are building this part in this manner, like this, by the robotic arm inside the liquid wet itself, then no support will be required and you will be able to grow the feature in the direction of the tool. And hence, you can see this is the part finally produced by appropriately tilting the robotic arm. So, this process they call as multi-tool and multi-axis computer numeric control accumulation for fabricating conformal features on curved surfaces. The another interesting system based on photopolymerization based liquid additive manufacturing is utilizing the two laser beam system. Opposed to the SLA and other similar method which we discussed so far, this method no longer works on the top of the surface of the wet. Instead, it works inside the volume, exists anywhere in the wet. So, like you see in this diagram, this is the conventional one. This is the conventional one, and this is the one which I am talking about and called as two laser beam system. So what happened in the conventional system, you are able to only write on the top surface of the liquid bed, while in this system you can write anywhere inside the liquid bed. How it happens? So in this case, two laser beams are used. Wherever the two laser beams interact with each other, that portion only on the liquid photopolymer wet got polymerized. The remaining portion doesn't get polymerized. Therefore, by appropriately aligning the tip or the focal point of the two lasers inside the liquid bed, you can create your parts. It is also called as two-step photopolymerization. So, why it is called as two-step photopolymerization? Because in this case, we usually, the one laser used to bring the photopolymer at a certain level of energy by absorbing the appropriate photons, and when the same photopolymer absorb the another energy from the another laser, then only it reaches to the excited state and got cured, and hence start the photopolymerization. If only one energy is given, then the photopolymer will not get photopolymerized. So in this method, it is assumed that one laser excites molecules all along its path in the wet, while most of these molecules will return back to their unexcited state. So if one laser is exciting one molecule, only one laser I am talking about, the molecule may go here in the excited state, but after some time it will come back, and this time period is very short. Now only the liquid wet, which is also in the path of the another laser, will be further excited and will reach into the excited state, and they will initiate the photopolymerization process. On this basis, the resin cures at the point of intersection of two laser beams, while the rest lying along either of the two paths will remain in the liquid form. However, there are several challenges when we use this type of system. So the first problem associated with this system is the focusing problem. The focusing problem exists because each laser undergoes numerous refraction. Why? Because as the ray moves from the source in the air through the liquid resin. Therefore, non-uniformities in the refractive index of the resin are difficult to control and monitor. And there are main three reasons for that. So as there are different processes for curing, because the photopolymer here, for example, falling under the path of only first laser, they may get excited, right? The molecule will get excited. They will not get polymerized, but will get excited. And due to that, the refractive index of this particular medium will also change. Hence, you are assuming that first of all, the laser is going from the air to the liquid. It will definitely not go in the same line. It will refract away, right? Depending on the index. Again, this portion, as the molecule in this region are getting excited, further the laser may not go really in this line. It may further get deviated. Due to that, it will be very difficult to locate the exact location of the focal point inside the liquid wet. Also, we assume that the resin is everywhere homogeneous, but that is not the case. Due to the non-uniformity in the resin itself, the focal point will be very difficult to locate. Also, when the process keeps on going, the temperature of the wet photopolymer will increase. Of course, it will not get polymerized everywhere, but at least the temperature will increase. And due to increase in the temperature, the refractive index will definitely change. And as the index will change, we will never able to predict it accurately that where the focal point of the laser is going to be. The second problem is associated on how two laser beam moving at the high speed can focus to a very small and accurate point of interaction. The problem is compounded by the high energies required of the two lasers, which means that the two lasers will have very short focal length also. Thus, the distance of the or the volume which we are trying to build will be very small. Why so? If we have a high power laser, that means we have to increase the power density, and it is possible if we use the focal length, and further it will be converted to a very small diameter. As we are making it a very small diameter, this distance, the focal distance, is quite less in that case. As the focal distance is quite less, what will happen? This entire area, which is the half of the length of the liquid which we are going to cure, will be very less. What happened if we increase? Because this focal point may not be achieved and the laser may get diverted also. As a result, your interaction diameter will be larger than the focal diameter, and you will not get the maximum energy at this location. Also, as these beams are moving with a very high speed, it will be very difficult to locate the exact location of one beam, and we have to calculate the exact location of both the beams so that we can interact them appropriately at the desired location. Hence, the problem becomes very difficult to solve in this case. Also, the third problem is associated that it is not always the case that the molecules lying along the path of either laser beam will return to the liquid state. This means that the unwanted resin may be formed along the path of either one of the laser beams. Consequently, the cured resin may pose further problem to rest of the process, because the cured resin will absorb further energies, and you will not be able to get the energy at the another location with the same value which you were getting earlier. So, the process looks very promising, but there are several challenges associated with the two beam system. The next emerging SLA based system is volumetric stereolithography. This process is inspired by the holographic lithography operation. So, what happened in this process? A light is projected on a beaker kind of shape where the liquid material is available, and this projected light is having three orthogonal images. Those are interacting appropriately inside this liquid chamber. It keeps on rotating and the light keeps on changing as per the requirement at a particular layer, and the part is built. In other words, it is really a layerless operation. You need not to do the slicing in any direction. The growth of the object is conformal and it starts from the center, and that is why it is called as volumetric stereolithography. However, such setups are still in the laboratory level only and under the research. I have not found any commercially system available for this particular technology, but as it's an emerging technology, it worth our attention. Now let us discuss about a process which is not really based on the polymerization, but uses liquid as a raw material. That is freezing based liquid additive manufacturing. In other words, it is called as rapid freezing prototyping. So, most of the discussed polymerization based liquid additive manufacturing processes are quite expensive, and many of them generate substance such as smoke, dust, hazardous chemical etc., which are harmful to human health and the environment as well. Continuing the innovation is essential in order to create new rapid prototyping processes that are fast, clean and of low cost. Dr. Ming Liu of University of Missouri in the laboratory of virtual and rapid prototyping has developed an environmental friendly additive manufacturing process that uses cheap and clean material and can achieve very good layer binding strength, fine resolution and fast build speed as well. They have invented such a process called as rapid freeze prototyping (RFP) that can make three-dimensional ice parts of arbitrary geometry layer by layer by freezing of two droplets. It consisted of the following four subsystems. The first one is a 3D positioning subsystem. Second is a liquid deposition subsystem. Third is freezing chamber, and fourth is the electronic to control the device. In this case, the XY table on which we are trying to build the part is completely kept inside a freezer. Then through the two nozzles, one for the main material and another for the support material, deposited the water material on the substrate. As the water falls onto the substrate, it got freeze. Wherever required, the main material is deposited. Wherever required, the support material is deposited. The difference between the main material and the support material is, the support material is also water, but it is mixed with some impurities like sugar. If we mix the impurities with the water, the melting temperature reduces. Instead of melting at 0 degree, the water with the impurity get melt at the lower temperature. And hence, for example, if the water is to be melted at 0 degree centigrade, the water which is mixed with the impurities will get melted at the lower temperature, assume at -4. As a result, at -4 degree centigrade, you will have a ice pattern of pure water. So based on this principle, the system looks like this. The entire XYZ table is kept inside the freezing chamber under a very low temperature up to -20 degree centigrade. The part is mounted on the Z axis like you see here. And after deposition of each layer, the elevator moves down by the desired layer thickness. As I have mentioned, the fallen droplets freeze immediately by convection through the cold environment and conduction by the previously frozen layer. So conduction happen in this direction and convection all over into the freeze. As you can see here, there could be two types of delivery nozzle. One is the continuous nozzle, another is drop on demand nozzle. In the case of drop on demand nozzle, we transfer the material in the drop by drop manner on the substrate, while in the continuous nozzle, the continuous material is supplied onto the substrate or the pre-built layer. Now to produce the overhang or undercut feature, like I have explained, a support material is deposited in the required region. The build material should be a pure water and the support material is eutectic sugar solution with the water, or which is called as saline water. So as you are seeing here, this blue nozzle, it is depositing the pure water and this green nozzle is depositing the saline water. At -20 degree, both of them will be in the solid form after deposition on the substrate. Now if I increase the temperature and bring it to -4 degree centigrade, the support material will go away, while the liquid material, which is pure water, will sustain at -4 degree centigrade, and that will be nothing but your ice pattern. The same you can see in this diagram also. This is the part produced. It is along with the support right now here everywhere. This is the support material, nothing but the water mixed with sugar. And if I further increase the temperature, assume that this is at -20 degree centigrade, and if I increase the temperature and bring it back to -4 degree centigrade, the support material just washed away and you have your final product in the solid form. Now what is the application of these ice patterns which we are making? You can use it for many purposes, definitely for prototyping, but also this ice pattern can be used for the casting purpose. Like you can just keep these ice patterns and pour the POP, for example, on the top, and everything is happening, assume that in a freezing environment. After pouring the mold over it, you can sublimate the ice directly into vapor. So to do that, you also need vacuum. So you keep everything, all the system inside a vacuum chamber and increase the temperature. If you increase the temperature at lower pressure, then the ice doesn't convert into water. It directly converts into the vapor, and the process is called as sublimate. In that way, you can replicate the features from the ice to the mold very accurately. Because if you convert it to water and water has the flow like properties, that may destroy those features. Instead, if you directly convert it to vapor, the features will remain there. So, that is one of the application of the rapid freezing. So, with this we have discussed all the liquid based additive manufacturing processes. Mainly those are based on the polymerization and freezing. Now, we shall discuss from the further lectures the solid based additive manufacturing process, and we shall start with the sheet based processes. With this, thank you very much.